This is the story of one Japanese engineer who solved a problem that had Detroit's best minds stumped for over a decade. A problem so fundamental that GM, Ford, and Chrysler collectively burned through nearly $1 billion trying to crack it, only to walk away with nothing. His name was Kenichi Yamamoto, and the solution he found was hiding in a material nobody in the automotive world had bothered to consider. By 1963, the Rotary engine had become Detroit's great humiliation. When Felix Wankel unveiled his revolutionary engine design in 1957, it promised everything American automakers craved: incredible smoothness, fewer moving parts, compact size, and power potential that embarrassed conventional piston engines. NSU's calculations suggested a rotary the size of a watermelon could match a V8 twice its weight. The licensing frenzy that followed was immediate. General Motors paid NSU $2.5 million for rotary development rights. Ford followed with their own multi-million-dollar deal. Everyone assumed America's industrial giants would cross the finish line first. The problem was the apex seal, a tiny triangular component smaller than your thumb that had to maintain perfect contact with the rotor housing while enduring temperatures exceeding 1,300 degrees Fahrenheit, pressure differentials of 1,000 psi, and sliding velocities that destroyed conventional piston rings. Detroit attacked it with brute force. GM tried cast iron seals with chrome plating, which failed at 5,000 miles. Ford experimented with tool steel alloys hardened to 60 Rockwell C, surviving just 7,500 miles before chattering apart. Chrysler went exotic with tungsten carbide in ceramic compositions, which either shattered or ground grooves into the housing. By 1963, an internal GM memo described the apex seal problem as insurmountable with current materials technology.
6,000 miles away in Hiroshima, a 39-year-old engineer named Kenichi Yamamoto was staring at the same problem with completely different eyes. Toyo Kogyo, the company that would become Mazda, had licensed the rotary technology from NSU in 1961, betting the company's entire future on making it work. President Tsuneji Matsuda had declared that Toyo Kogyo would either succeed with the rotary or cease to exist as an independent company. Yamamoto was put in charge of a team of 47 engineers called the Rotary 47, and the apex seal was their entire world. Yamamoto's background set him apart. He'd studied mechanical engineering at Tokyo Imperial University, but had spent years working on industrial furnaces and high-temperature materials. Where Detroit's engineers kept searching for the perfect metal, Yamamoto asked a different question entirely. Why did it have to be metal at all? His team began experimenting with carbon-aluminum composites, materials more common in industrial applications than in automotive engines. Carbon offered self-lubricating properties. Aluminum provided thermal conductivity. The breakthrough came in late 1962 when Yamamoto's team developed a proprietary process that embedded aluminum particles within a carbon matrix and reinforced the structure with hair-thin steel fibers. The composition was 70% high-density carbon, 25% aluminum powder, and 5% steel fiber reinforcement, pressed at 2,000 tons per square inch and centered at 800 degrees Fahrenheit in an inert atmosphere.
What happened next defied everything Detroit believed about engine materials. Yamamoto's carbon aluminum seals got better with use. The carbon gradually polished the chromed housing surface while depositing a microscopic lubricating layer. The aluminum conducted heat away from the seal face. The steel fibers maintained dimensional stability under load. Testing began in early 1963, and the first prototype ran for 100 continuous hours, already exceeding anything the Americans had achieved. Then 200 hours, then 300, then 400. When they finally tore the engine down, the apex seals showed minimal wear, and the housing surface looked better than when they'd started. Yamamoto's team kept pushing. Adding less than 0.5% antimony increased the seal's high-temperature stability by 40%. A multi-stage sintering technique created a gradient structure, harder at the surface and more flexible at the core. By mid-1963, the seals were surviving 1,000-hour durability tests, equivalent to 60,000 miles of driving. Meanwhile, a December 1963 internal GM report stated that the Japanese approach, using carbon-based materials, represented a fundamental misunderstanding of internal combustion requirements. Ford's engineers called it technically naive. Production of the Cosmo Sport began in May 1967, making it the world's first mass-produced rotary car. The 10A engine displaced just 982 cc, but produced 110 horsepower at 7,000 RPM, a specific output of 112 horsepower per liter that embarrassed contemporary American V8s, making around 60 horsepower per liter. The engine weighed 224 pounds complete. A comparable piston engine making the same power would have weighed close to 400 pounds. Mazda backed it with a 50,000-mile warranty on the apex seals, at a time when most manufacturers wouldn't guarantee piston rings past 24,000 miles. Road and Track called it the most significant advancement in internal combustion technology since the turbocharger.
Detroit panicked. GM purchased 3 Cosmos through intermediaries in Japan. Ford bought 5. When engineers tore the engines down and found Yamamoto's carbon aluminum seals, the reaction was equal parts amazement and embarrassment. A GM engineer who worked on the teardown later described it as spending years trying to build a better hammer when what was actually needed was a screwdriver. By 1968, GM had spent an estimated $100 million on rotary development with nothing to show for it. Ford had burned through $75 million. Chrysler had written off $50 million. Mazda, working with a development budget that was a fraction of any single American manufacturer's expenditure, had already put the solution on the road. GM's response was the Rotary Vega, announced in 1970 with promises from President Ed Cole that it would make every other engine obsolete. Their apex seal solution was a 3-piece design, combining a cast iron base, a ceramic insert, and a tungsten carbide tip. In theory, it combined the best properties of each material. In practice, different thermal expansion rates caused the pieces to separate at high temperatures. The assembly was nearly impossible to manufacture consistently, and each seal cost $400 to produce, 40 times more expensive than Yamamoto's design. In September 1974, GM quietly canceled the program after spending another $300 million and producing exactly 0 production engines. Ford shelved their rotary project in 1975 after $400 million in total development costs. Their final benchmark of a 1974 Mazda RX-4 found the apex seals within factory specifications after 150,000 miles of testing. Ford's best experimental seals were failing at 20,000. The RX-7, launched in 1978, became the ultimate vindication, reliable enough that Sports Car Club of America had to ban it from certain racing classes for dominating the competition. By 1980, Mazda had sold over 1 million rotary-powered vehicles worldwide. The apex seals that Detroit had declared impossible were routinely surviving 200,000 miles in street use. At Le Mans in 1991, the Mazda 787B, powered by a 4-rotor R26B engine running Yamamoto's evolved apex seal technology, didn't just compete against Porsche, Mercedes, and Jaguar. It won outright,
screaming to 10,500 RPM and producing 700 horsepower from just 2.6 liters. Rotary engines were banned from Le Mans the following year. The technology had been so successful that racing organizers had to outlaw it to give everyone else a chance. The financial reckoning was stark. Combined, American manufacturers had spent nearly $1 billion trying to solve a problem Yamamoto cracked on a fraction of that budget. An automotive news analysis from 1985 found that if GM had simply licensed Mazda's Apex Seal technology in 1968, they could have had rotary engines in production by 1970 for less than $50 million total. Instead, pride cost them 20 times that amount. Yamamoto passed away in 2017 at age 95, having spent his entire career at Mazda. The New York Times called him the engineer who proved Detroit wrong, but that undersells what he actually accomplished. He didn't just find a better seal. He changed how the entire industry thought about material selection, proving that composites, ceramics, and hybrid materials had a place inside a combustion engine. The carbon-aluminum principles behind his Apex seals echo through modern Formula One brake discs, high-performance pistons, and electric motor bearings. The lesson isn't just about Apex seals. Detroit threw money and conventional thinking at a problem and got nothing. Yamamoto questioned the assumption that metal was the only answer, looked outside automotive engineering entirely, and solved it. Sometimes the way things have always been done is simply not the way they need to be done, and sometimes all it takes is one engineer willing to ask a different question.